Hi, welcome to part 2 of Lecture 13 on gravity. So what I want to cover now is how Newton developed his law of gravity and then how he used it to derive Kepler's 3 laws and expand and improve upon them. Kepler had used his laws derived his laws solely using planetary data, planets orbiting our sun. It's a very lopsided scenario where one object, the sun, has an enormous mass, and the other object, the planet, has a very, very tiny mass. And so Kepler was not able to see some of the nuances that Newton was able to derive from theory. Just using his laws of motion in combination with his new law of gravity, he was able to show that there were more elements to Kepler's laws than Kepler had seen. So in deriving his law of gravity, Newton came about it by way of an insight, a very dramatic insight. He was thinking about the moon's orbit around the Earth, and so this little animation here sort of represents that. I've got a large mass of the Earth, I've got a much smaller mass orbiting around it, and the small mass appears to be moving in a fairly circular orbit around this red point. That's the true center of the circle of the small mass's orbit. But that red point is deep inside the larger object. So for all intents and purposes, it looks like the small object is orbiting the larger object. And Newton thought about this as just, so here's the moon. It's orbiting the Earth. The moon has a nearly circular orbit, not a perfect circle, but a nearly circular orbit around the Earth. And by deriving his first law of motion, Newton had shown that if you're going to move in a curved path, you have to have an unbalanced force. If you have an unbalanced force, you have an acceleration. And an acceleration is what turns the velocity of the moon. So if I drop a red arrow to show the moon's instantaneous velocity right there at the top point of the orbit, so there, when the moon is right there, that's its current velocity. And that's true for every point in the orbit. The instantaneous velocity, when the object is at that point, the velocity arrow is parallel to the circle right at that point. But then at some later point, the red arrow would be tilted downwards. So something must have yanked that arrow over. And as we saw with our automobile examples last lecture, that's an acceleration. If I want to make something turn, I need an acceleration. If I don't have an unbalanced forces create accelerations. So if I have no acceleration, if I have no unbalanced force, an object is going to move in a straight line at constant speed. That's Newton's first law. So I need this acceleration to make the moon turn. And because the moon's orbit is so circular, the acceleration is always pointing near the center of the orbit. And what is near the center of the moon's orbit? The Earth. The moon's orbit is elliptical enough that the two focus points are separated out from the center, but all astronomical measurements clearly showed that the Earth was located extremely close to one of the focus points of the moon's elliptical orbit. The moon appeared to be behaving according to Kepler's first law, just orbiting the Earth rather than orbiting the sun. So Newton's thinking, well, if I'm going to make the moon orbit the Earth, I need an acceleration that points towards the Earth. And that means there's an attractive force towards the Earth. And already in Newton's day, Newton's law of gravity, Newton discovered his law of gravity, but what that means is that he discovered an equation to describe gravity. He didn't invent gravity. He didn't invent the word gravity. It already existed in English language. It comes from the same Latin root as the word for grave. Something on the surface of the Earth, everything on the surface of the Earth is attracted downwards towards the Earth, into the Earth. When you die, you're buried, you go into the Earth. You go into your grave. gravity is a pull into the Earth. And so people already knew about gravity. People had described gravity. Galileo had done lots of experiments showing different massed objects with different weights fell at the same rate due to gravity. The acceleration due to gravity was a constant. Newton knew all these things. His great insight was like, well, wait a minute. Apples near the surface of the Earth get drawn towards the center of the Earth. The moon orbiting the Earth appears to get drawn towards the center of the Earth. Maybe, just maybe, it's the same force. It's the same phenomenon. What we call gravity on the surface of the Earth, things drawn to the surface of the Earth because they're really drawn to the center of the Earth, below the surface of the Earth. Maybe that gravity, the thing we call gravity, that attraction we call gravity, is universal, and that's what's holding the moon in orbit around the Earth, and that's what's holding the Earth in orbit around the sun. Just one phenomenon that we already call gravity when we talk about it on the surface of the Earth. And so that was his question. Could it be the same attractive force holding the moon in orbit, the same force that makes an apple fall to the ground? And so he asked himself, well, if this is the case, then what does it imply? What would it require? How would the force have to act? And so he calculated how much acceleration the moon needs to stay in its orbit. And so he knew from astronomical measurements of his day, they knew the radius of the moon's orbit from one location on Earth. From you wait for the night of the full moon and you measure the position of the moon in front of the stars just after sunset, at midnight, just before sunrise. You correct for the moon's orbital motion, and you can measure the parallax shift of the moon from you being on one side of the Earth underneath the moon to the other side of the Earth, and that'll give you the distance to the moon. So they had a fairly accurate distance to the moon. He knew it was a few 100,000 miles out to the moon. And he knew the period of the moon. To go 360 degrees around the Earth takes 27.3 days. And so from that, from those two numbers, and from his laws of motion, he had already figured out how to calculate the necessary acceleration. How many meters per second does the moon have to be falling towards the Earth in order to give it its current orbit with a radius of 230,000 miles and an orbital period of 27.3 days. And so if we look at a figure here, here's the Earth. The blue disk is the Earth. There's the center of the Earth. I've got an apple near the surface of the Earth, and so the apple's distance from the center of the Earth is the radius of the Earth plus a few meters. And the radius of the Earth is several million meters, so the few meters of the apple's extra height above the surface of the Earth is ignorable. The apple's distance from the center of the Earth is the radius of the Earth. Newton knew the radius of the moon's orbit, and he had already calculated from his laws of motion that the inward acceleration, the centripetal acceleration, is going to be the velocity of the thing moving in a circle squared divided by the radius of the circle. And so he knew that things fell to the surface of the Earth at 9.8 meters per second squared. Galileo and other people had already measured that. He was able to calculate the acceleration at the moon's orbit and found that it was 1/3,600th. More than 3,000 times smaller, but not quite 4,000 times smaller than the acceleration of the apple. So this golf ball falls 3,600 times faster. Its acceleration is 3,600 times greater than the moon's acceleration. The moon is turning very, very slowly. It takes 27.3 days to make one 360-degree orbit. So the turning rate of the moon's orbit is relatively slow. The acceleration is not that dramatic. A few inches per second, essentially. And what Newton did that was so great, so amazing, was he noticed a coincidence that if he took the ratio of the Earth's radius to the radius of the moon's orbit was 60 times larger than the radius of the Earth. But the acceleration at the moon was 1/3600th. And 3,600 is suspiciously 60 squared. So he realized then that gravity gets weaker with distance. And it gets weaker with the square of the distance. Gravity is inversely proportional to the distance squared. So in moving outward from the center of the Earth to the surface of the Earth, I've gone a few thousand miles. In going from the center of the Earth to the distance of the moon, I've gone several 100,000 miles, 60 times further. And gravity has gotten 60 squared times weaker. And so, gravity is an inverse square. Gravity is directly proportional to 1 over r squared. So he's trying to figure out an equation for the force of gravity. And one thing he knows now is that it's going to involve the square of the separation between the two objects. So here's object number 1, and there's its center. Here's object number 2, and its center. And r is the distance between the centers. And the force of gravity is inversely proportional to r squared. If gravity is what makes the moon orbit, as well as making apples fall, then it must follow that relationship. And then he said, well, wait a minute. When things fall to the surface of the Earth, if I have a very light spongy ball and a heavier golf ball, so lighter mass, heavier mass, they hit the table at the same time. Let me watch the video there. They hit the table at the same time. So, and Galileo had shown that that's true for all sorts of masses. If you have a compact mass that avoids significant effects from air friction, everything falls at the same rate. So, if everything falls at the same rate, then when I'm at the surface of the Earth, the mass must be in the force of gravity. The mass of the apple has to be in the force of gravity because see, how am I going to do this? I'm going to erase this for a moment. Force is equal to mass times acceleration. That's his second law of motion, Newton's second law of motion, F equals ma. But if I'm talking about the force due to gravity, everything accelerates to the Earth at exactly the same rate. And so that means that the force due to gravity has to have this m in it. The m of the falling mass has to be in there, and the force has to be directly proportional to it. The acceleration depends on the distance squared, but the force itself has to be directly proportional to that smaller mass because everything falls at the same rate. This is just equal to m times g. And then no matter what object I'm dropping, the a is equal to g because the m cancels on both sides. And so the falling mass is in there. And then Newton applied his third law of motion. So To derive the law of gravity, he's using all three of his laws of motion. The moon is turning, so it has to have an inward acceleration. That's the first law. Everything at the surface of the earth falls at the same rate, so the force of gravity has to be directly proportional to the falling mass, or else heavier things would fall faster than lighter things. And then finally, he applies his third law. If the Earth's gravity is going to pull the moon into its orbit using an equation like this with some more unknown stuff in it, then his third law demands that the moon's gravity is going to pull on the Earth. And in that scenario, the Earth is the falling body. If I'm looking at this force as being the force of the Earth pulling on the moon, then this m is the moon's mass. But if I trade the scenario around and think of this force as the moon's pull on the Earth, then this m has to be the Earth's mass. But those two forces have to be equal to each other. The force of the Earth attracting the moon by his third law has to exactly equal the force of the moon attracting the Earth. And so this force has to have the moon's mass in it. This force has to have the Earth's mass in it. So I must have two different masses in the force of equation. The thing that's doing the attracting and the thing that's being attracted. Both masses are in there. That's the only way to make everything fall to the ground at the same rate here at the surface of the Earth. But it's also the only way for the third law, for Newton's third law of motion, to work between the Earth and the moon. And so, again, this is all predicated on just assuming that the pull that keeps the moon in orbit is the same pull that makes apples fall to the Earth. It's all gravity. And so, looking at his units, it's like, well, I've got a mass, I've got a distance squared. Those aren't the units of force. I'm going to need some sort of numerical constant that gives me the right units. And so he was thus able to derive his law of gravity. Just with the simple assembly. He knew his three laws of motion already. He assumed those were true and universal. He knew from Galileo's experiments that everything fell to Earth with the same acceleration, which showed that the force of gravity had to involve the mass of the falling body, or else falling bodies, more massive bodies, would fall faster. And he figured out from this the fact that apples fall to the Earth at 3,600 times faster acceleration than the moon is falling towards the Earth to keep it in its roughly circular orbit around the Earth. And so combining all of these observations together and assuming that his three laws of motion had to be true in every possible situation, that they were universal laws, he got this equation for gravity. And once he had this equation for gravity, he could then combine it with his laws of motion and calculus, the mathematics of calculus, and derive the orbits of the planets and predict their future motions. And sure enough, he could do it spot on, accurately. This appeared to be the right equation. This one equation now explained apples falling to trees, cannonballs shot out of cannons, birds flying through the air, pellets, bird poop falling out of birds, and the moon orbiting the Earth and the planets orbiting the sun. And once he published this law, his colleague Edmund Halley used it to derive the orbit of the comet that now bears his name, periodic comet Halley, Halley's Comet. Halley was able to show that, well, there's been a comet seen almost like clockwork every 76 years in history. It was seen the year that Julius Caesar was assassinated. And then roughly every 76 years ever since. Sometimes it wasn't seen, but you could explain that by when it was close to the sun, it was on the opposite side of the sun from the Earth, and so it wouldn't have been seen. It would have been up in the daytime when it was bright. So the law of gravity seemed to work for everything in the solar system as well as for everything on the surface of the Earth. And so since the acceleration of an apple is just equal to g, which is a constant for everything falling to the surface of the Earth, and since F equals ma, g is the same thing as a, they're accelerations, so the force of gravity must involve the mass of the falling object. And so the force must be directly proportional to the target mass, but then his third law requires, by symmetry, that if the Earth's gravity requires the moon's mass and the moon's gravity requires the Earth's mass, but both forces are going to be exactly identically equal, they have to involve both masses. Each one of them has to have both the Earth's mass and the moon's mass in it. And so he derived this equation. The force of gravity, F, between two objects is directly proportional to each mass involved, m1 and m2. Subscripts are just labels. By tradition, we put the more massive thing as m1, but if I'm talking about the Earth and the Moon, I can just call it m sub Earth and m sub Moon. If I'm talking about Jupiter orbiting the Sun, m sub Sun and m sub Jupiter, I can call them whatever I want. They're just labels. But the force of gravity is directly proportional to each mass, call them m1 and m2, and the force of gravity is inversely proportional to the square of the radial distance between their centers. And that's another great realization that Newton had. An apple falling to the Earth, there's the center of the Earth, there's my apple. The appropriate distance is not the distance of the apple from the surface of the Earth, it's the distance from the center of the apple to the center of the Earth. That's the key distance. And so I have two objects, could be the Earth and the Moon, the Sun and Jupiter, the Earth and an apple. Doesn't matter what the two objects are. I take the center of the one object and the center of the second object and the distance between them. I call that r. This is m number 2, that's mass number 1, and the force of gravity is just simply directly proportional. The force is directly proportional to m1, the force is directly proportional to m2, the force is inversely proportional to the distance between them squared, and then I have a constant out front to make the units work. These units need to be force units, which are newtons, but this has kilograms, this has meters, and it's squared. So this has to have units of newtons in its top, 2 kilograms in its bottom, and meters squared in its top, so that all of these units disappear. And when we do sophisticated laboratory experiments to measure this, Newton racked his brains with ways to try and come up and measure what this constant was. And he was able to deduce that it's a really tiny number. And using the tidal forces on the Earth, how much force does it take to raise the ocean tides 3 feet and settle back down at low tide, 3 feet below average, 3 feet above average at high tide? What sort of force does that take, given the mass of the Earth, the mass of the Moon, the radius? He didn't know these masses very well, but he made some estimates and guesses. He knew how dense rock was, so if he assumed both of these bodies were just made of solid rock, he could estimate their masses and then estimate g, and he came out with a really tiny number. But it wasn't until almost 150 years after Newton lived before a scientist accurately measured it in a controlled laboratory experiment. And we now know today that this is the accurate value for Newton's constant g. 6.67 times 10 to the minus 11th. 10 to the minus 11 is minus 9 minus 2. And 10 to the minus 9 is 1/1,000,000,000th. 10 to the minus 2 is 1/100th. So this is 1/100,000,000,000th. 600 billionths of a Newton meter squared per kilogram squared. It's an incredibly tiny number, gravity is enormously, enormously weak. And I can demonstrate that fairly easily because, let me find, there we go. I have a metal paper clip here. Let me get closer to the camera. I have just a metal binder clip here. Nothing special about it. It's made out of iron. I have my whiteboard erasing cloth, which has a magnet in it, a magnet about the size of a nickel. Here's my piece of metal. I would estimate maybe it's a few ounces, so it's 10, 15 grams worth of metal. The entire Earth, the entire enormous mass of the Earth, 10 to the 24 kilograms of mass in the Earth, is pulling this thing downward with the Earth's pull of gravity. So the M1 in my equation for the Earth is huge, just enormously, enormously huge, and yet my nickel-sized magnet can easily overcome it. The magnetic force of attraction is enormously stronger than the force of gravity. Kilogram for kilogram, cubic centimeter per cubic centimeter, anything that generates an electrical attraction like static electricity or a magnetic attraction like a bar magnet can easily overcome gravity. Gravity is the weakest force in the universe. There are 4 fundamental forces in the universe. 2 of them, the strong force and the weak force, only operate inside atomic nuclei. So they don't work outside of atoms. They're only working at the very, very, very tiny centers of atoms. And then the other 2 forces are electromagnetism and gravity. In electromagnetism, its equivalent constant is a factor of 10 to the 40, larger than gravity, which is why this tiny magnet can overcome the entire gravitational pull of the Earth so easily. But despite being so weak, gravity is the only physical force that can reach out over literally infinite distances. Gravity gets weaker and weaker and weaker as it goes out, but it never goes to zero. So 1,000 light years from the sun has a pull of gravity. Incredibly weak, but it's there. The Earth has a pull of gravity at 1,000 light years. Incredibly weak. 300,000 times weaker than the sun's gravity at that same distance. But it's still there, and anything floating in outer space is floating in outer space. There's no friction. There's no solid thing like a table to give you a balancing force to resist gravity. And so no matter how weak the gravitational pull is, you're going to feel it. And you're going to move. You're going to move incredibly slowly, but you're going to move. And none of the other physical forces has that tremendous range. Electromagnetism has positive and negative charges that attract each other. So from a great distance away, there's equal numbers of positives and equal number of negatives. From a great distance, the charge tends to be neutral. And so there's just not a strong force, a strong reach to the electromagnetic force over great distances. Gravity is the only thing that can reach significant strengths over large distances. All right, so he's got an equation for the law of gravity. He's got equations for his laws of motion, particularly the second law of motion is itself an equation. The third law of motion lets you take 2 forces and set them equal, so you can turn that into an equation. Combining all these equations together with calculus, he's able to calculate lots of interesting things. And so one question he had was, can I can measure the moon's orbit, but can I predict what the moon's orbit, I can measure the moon's orbital speed. 2,800 miles per hour is the moon's orbital speed. can I predict what the moon's orbital speed would be if it had a different orbit? If it had a larger orbit, a smaller orbit, a more elliptical orbit? Can I predict what its orbital velocity would be? And so one of the things he was able to derive from his force of gravity, using the laws of motion, was to predict how fast something should be orbiting in a circular orbit around a large mass. So here I've got a small thing orbiting a large thing. Its orbit has a certain radius. Its orbit has a certain orbital period. And so from that, I can just take the circumference of the orbit and divide it by the period, and that's the average speed. And if the orbit is a circle, the average speed is constant. It's just a constant speed. The average speed is the orbital speed at all points. So, and this is around a big mass, capital M. And as long as you assume that the small mass, M2, called little m, as long as it is sufficiently tiny compared to this one, as long as it's more than 100 times smaller, then this equation works out just fine. And it turns out that the circular orbital velocity of something small orbiting a very large mass, the only two variables that are important are the size of the large mass, how much material is here generating a gravitational pull, and if you're in a circular orbit, you have a fixed distance away from it, what's your orbital radius? Take Newton's tiny gravitational constant, multiply it by the mass, divide it by the distance, take the square root of that fraction, boom, you've got the circular velocity in a circular orbit. Now, most orbits aren't perfect circles. They're close. Major planets have orbits that are close to being circular, but not exactly. But asteroids, and particularly comets, don't have circular orbits. But Newton was also able to show that this circular orbital velocity is also the average orbital speed in any elliptical orbit. So when your radius from the focus point is equal to a, you're located at the end of the minor axis. So if I draw my ellipse, there's my ellipse, there's my major axis, there's my minor axis, there's one focus point, there's the empty focus point. I'm going to be moving fastest when I'm here. I'm going to be moving slowest when I'm here. When I'm here, my distance from that focus point to that focus point has to equal, always, no matter where I am on the orbit, it has to equal the full major axis. The full major axis is 2a, which means that one is a and that one is a. So when I'm either here or here, when my orbiting body is at the ends of the minor axis, I am the semi-major axis away from the body that I'm orbiting, and that means I'm at my average distance. Averaging, this is the smallest distance, this is the largest distance, that's the average distance over the entire orbit. And if this is when I'm moving fastest and this is when I'm moving slowest, Kepler's second law demands that when I'm at my average distance, I'm also at my average speed. And Newton was able to show that this equation gives you that average speed. Even in an elliptical orbit, this is the average speed in the orbit. So it's a useful number. A comet will have an incredibly high speed when it's close to the sun and incredibly slow speed when it's far from the sun. But if I'm just interested in its average speed, I can use this equation. The comet doesn't have a circular orbit, but this equation gives me the average velocity of an elliptical orbit, as well as the constant velocity of a circular orbit. And then Newton also asked himself, if this is how fast I need to go to stay in a circular orbit. If I'm going slower than that, as we saw in the last video, if I'm going slower than that, I'm going to be in an elliptical orbit that either just misses the Earth or collides with the Earth. We'll get more and more elliptical. If I start here and I slow the speed down, I'll get more and more elliptical, where this is the point where I'm furthest away from the Earth. What happens if I start here and I speed the speed up greater than this circular velocity? Well, it turns out I create an ellipse where this is the point where I'm closest to the Earth. And if I keep speeding it up and keep speeding it up and keep speeding it up, what's going to happen? This was Newton's question. What happens if I keep increasing the orbital velocity larger than the circular velocity? So I pick a distance, I start at that distance, and I keep increasing the horizontal speed, the orbital speed at that distance. What happens to the resulting shape of the orbit? And what he found out was that there's a limit. The orbit, as you increase the speed above the circular velocity, the orbit keeps getting more and more elliptical, more and more elliptical, more and more elliptical. So I'm going to turn that diagram 90 degrees. So here's the Earth. Here's my starting radius. If I start at zero velocity, boom, I just fall straight down and hit the Earth. If I start with enough velocity, I can just miss the Earth and come back. So I'm in an elliptical orbit where this is my apogee point, furthest away from the Earth. If I give myself just the right amount of velocity, I can create a circular orbit around the Earth. And if I give myself more velocity, I create an elliptical orbit where that's the point where I'm closest to the Earth. So now I'm starting at my perigee point. And if I give myself more velocity, I just make that ellipse more and more and more elliptical. And Newton found that there was a limit. There was a point where you'd go out. As I kept increasing the speed here, the apogee point kept getting further and further and further and further away from the Earth. And there was a limiting speed where the apogee point would go to an infinite distance away from the Earth. Meaning the object would start here and fly away from the Earth, but never come back. It would escape the Earth's gravity. And so Newton asked himself, well, can I calculate an equation that will tell me that? What is the escape velocity from the Earth? And so given a large mass, capital M, and a starting distance r, we can find the speed necessary to completely break free of the gravity of m, and we call this the escape speed, the escape velocity. And the equation is quite simple, surprisingly simple. It's the circular velocity with a 2 stuck inside the square root. So it is square root of 2 larger than the circular velocity of an orbit. If I start with an object that's already in orbit, I only need to speed it up a little bit, not tremendously. I don't even need to double its speed in order for it to escape. If it's already in a circular orbit, I just need to increase its speed by the square root of 2. The square root of 2 is 1.41, so I just need to speed it up 41% over its normal circular speed, and it will just break free of the Earth's gravity. So I start there at r. If I give myself the escape speed, I'm going to fly away into space and never come back. And the escape velocity, note the proportionalities here. The escape speed is directly proportional to 2, that's a constant. It's directly proportional to g, that's a constant. So they never change. It's directly proportional to m inside the square root. So As I increase m, v escape will also increase, but not as fast. If I made m 4 times larger, the factor of 4 inside the square root of 4 is 2, the escape velocity would only get twice as large. So if I made the mass 4 times bigger, my escape velocity is only 2 times larger. If I make the mass 100 times bigger, you'd think it would be 100 times harder to escape. But if I make it 100 times bigger, the square root of 100 is 10. This whole fraction only got bigger by a factor of 10. So the escape speed would only be 10 times larger, despite using 100 times more mass. But the more massive something is, the harder it is to escape. The closer you are to something, the smaller r is, the harder it is to escape. That's because gravity is stronger the closer you get. So if you start out closer, you have to work harder to break free. So the escape velocity is inversely proportional to r inside the square root. So again, if I make r 100 times larger, it's inverse proportionality, so v escape is going to get smaller, but the change of 100 is inside the square root, so it's going to get 10 times smaller. 10 times larger, sorry. I make this 100 times smaller, this gets 10 times larger. I make this 4 times larger, this gets 2 times smaller. So more mass is harder to escape, and a smaller radius, closer in, it's harder to escape. Those are the two key properties that relate to escape speed. So here we have the Earth looking down on the North Pole. I have a rocket ship that's already in a circular orbit around the Earth. Let's say the International Space Station is already in orbit around the Earth. So if I launch the raw materials up to the International Space Station, if I bring a whole bunch of metal parts and a whole bunch of circuits and a whole bunch of fuel up to the International Space Station, and I have the astronauts that are on the International Space Station build a space probe with a rocket engine and a fuel tank, and they assemble the space probe on board the International Space Station, then the International Space Station is already orbiting the Earth at 17,500 miles an hour, as I covered in the last video. The circular orbital velocity at the 200-mile altitude orbit of the International Space Station above the surface of the Earth, the circular orbital velocity there is 17,500 miles per hour. To break free of the Earth's gravity at that distance, I need to move outwards into space at around 25,000 miles per hour. But if I build my space probe on board the International Space Station, I'm already moving 17,500 miles per hour. I just need to give it an extra boost of a few thousand miles per hour to get it to break free of the Earth's gravity and escape into outer space. So once the space probe is outside the International Space Station, they fire the rocket, and as the rocket is firing, it's constantly raising its orbit to a bigger and bigger radius, and with enough thrust, it just follows this parabolic path outwards into space. And so, as I pointed out, though, the escape velocity is only the square root of 2 larger than the circular velocity. And the square root of 2 is 1.41. And I'm multiplying by the square root of 2. I'm multiplying by 1.41. Multiplying by 1 doesn't do anything. So I'm really, in terms of increasing something, I'm making it 0.41 times larger. And so 41% larger than the circular velocity is my escape velocity. Putting the raw materials into orbit on the International Space Station to build the space probe, there I've already done 71% of the work I need to get into outer space, to break free of the Earth's gravity and go to Mars, or go to Jupiter, or go to Pluto. Now, once I break free of the Earth's gravity, I have to keep in mind that I'm now 1 astronomical unit away from the sun, and the sun has a pull of gravity. So if I want to escape the solar system, I need to break free of the sun's gravity at that distance. And so there's another few tens of thousands of miles per hour necessary. If I'm just going to the moon, I need around 25,000 miles per hour of speed. If I'm going to Mars, I need more than 25,000 miles per hour of speed. If I'm going to Pluto, I need to almost nearly break free of the sun's gravity at the distance of the Earth, and so I need much more speed to do that. And the other cool thing about the escape velocity equation is what came about from Einstein discovering his theories of relativity. One of the key underlying principles of Einstein's theories of relativity, and something that has been tested over and over and over again in hundreds of different physical experiments over the last century, is the fundamental assumption that nothing can travel faster than the speed of light. So it begs the question, can I make something that I could not escape from? In order to escape from something's gravity, I need a minimum speed. If I'm going faster than this speed, I can break free. If I'm going slower than that speed, I can't break free of the gravity. But there's a speed limit in our universe. You cannot go faster than the speed of light in a vacuum. You cannot go faster than 300,000 kilometers per second. It is forbidden. And physicists and astronomers have tested this over and over and over and over again, and we haven't yet found anything that can go faster than the speed of light in a vacuum. So, if there's a maximum speed limit to the universe, and if you want to break free of something's gravity, you have to go faster than this, what happens if I set that equal to the speed of light? If I ask myself, how massive would something have to be, and how close to it would I have to get, such that to escape from that point, I'd have to go at the speed of light, which means if I get closer, I'd have to go faster than the speed of light, and I'm absolutely forbidden to go faster than the speed of light. So if I get closer than the speed of light escape velocity distance, I'm trapped. I cannot escape. And so shortly after Einstein published his theories of relativity, several scientists started thinking about this problem, and a German scientist named Schwarzschild was the first person to publish a formal paper on it. And he coined the term a black hole. If I take a huge mass, something with the mass of the sun, the mass of an entire star, and I compact it down so that it's only about 10 miles across. At that point, 10 miles away from the center of something with the mass of a sun compacted to something smaller than 10 miles in diameter, 10 miles in radius, it under those extreme conditions, with a star's mass compacted into a ball 10 miles in radius, this equation is going to give me an escape velocity that's greater than the speed of light. And if you have to travel faster than light to get away from it, but you're forbidden to travel faster than light, you can't get away from it. It is a region of space where, as long as you stay away from it, you're fine. But the moment you get too close to it, you're never coming back out. You're trapped. It's like a hole. You wander around the outer edge of a hole, you're fine. You step off the edge of a hole, you fall into it. It's just that the laws of the universe are such that once you fall into a black hole, you're never coming back out. You cannot. To come back out, you'd have to go faster than the speed of light, and you can't do that. And another consequence of Einstein's theories of relativity is that light is affected by gravity as well. Light doesn't have mass, but under Einstein's description of gravity, gravity is a distortion of space, and light moves through space, so it feels the effects of gravity too. And using Einstein's equations of relativity, you find that this equation also predicts, this equation lets you predict the point of no return around the black hole, and if light goes inside that radius, if light gets too close to a black hole, it is also trapped. It can't get out either. And so for very, 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 very large m and very, very, very small r, the escape speed is greater than the speed of light. Nothing can go faster than the speed of light, not even light. And so nothing can escape from inside that small radius r, not even light. It is a three-dimensional sphere. So what Einstein's equations predict is that all the mass that you put here collapses down to a single mathematical point that we call the singularity, and then setting this equation, setting the v escape equal to the speed of light, rearranging the equation to solve for r, gives me the radius at which the escape speed is equal to the speed of light. And as long as I'm outside that radius, I can get away. It's going to be really hard. I'm going to have to travel at 80% the speed of light, 85% the speed of light, 95% the speed of light, 99% the speed of light, but that's still physically achievable. Light can do it. Light always travels exactly at the speed of light. So I can see if I dropped a camera with a repeating flash bulb and I let it fall into my black hole, I could see the flash, 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 see the flash. Nope, I can't see it anymore. It's gone. This event horizon, this is what we call the sphere. The point of no return is a three-dimensional sphere surrounding the singularity. We call it the event horizon because you can't see any event that takes place inside the bubble. You can only see events that take place outside the bubble. And so the bubble is the point of no return, and everything that crosses the event horizon is now sequestered in the singularity, never to come out again. And so it's this bubble is no longer part of our universe. It's a hole in our universe because anything that goes in is never coming back out to rejoin the rest of the universe. Crazy, crazy, crazy stuff. But we have found ample evidence of black holes in outer space. And so ultramassive, ultra-compact objects form these things that we call black holes in space. Any matter that falls in, any light that falls in, any form of information at all that goes across the event horizon, it can't escape from inside the event horizon. And the event horizon is the radius where the escape velocity is equal to the speed of light. And so I mentioned earlier, Einstein talks about gravity as a distortion of space. A black hole is such an extreme distortion of space that it's like a bottomless pit. I can orbit it out here and I'm fine. But if I get too close, whoop, I just fall down the pit and I never come back. I have left the universe. More importantly, I've been compacted like garbage in a garbage compactor, and I'm now here and I'm never leaving. And atoms and molecules just get completely destroyed, get turned into subatomic particles, which get turned into energy, which get just compacted, infinitely dense there at the center of the singularity. That's crazy. It's weird. It's unphysical in a whole bunch of ways, but we don't need to worry about it because we will never, ever, ever, ever see or measure or hear or taste or smell the singularity because no information can get out about it. So it's free to be as crazy it wants to be because inside the event horizon is no longer part of our universe. It's a simple way to think about it. So if light can't escape from the singularity, if light can't escape from anywhere inside the event horizon, how do you see these objects? When Schwarzschild first published his paper, he's like, well, this is an interesting theoretical idea, but I'm not convinced they really exist, because you've got to compact a huge amount of matter into a very tiny space. You've got to take something currently the size of the sun and make it the size of New York City. If I want to turn the Earth into a black hole, if I want to take the mass of the Earth and crush it down to a small enough radius so that the escape velocity is equal to the speed of light, I need to take the entire Earth and squish it down to the size of a grape. Less than an inch in diameter. And how could you possibly do that? Even in nature, how could you possibly do that? So Schwarzschild wasn't really convinced that they were real, but he also pointed out that even if they were real, even if there were black holes somewhere out in space, how are you going to see them? The only way we see things in outer space is from the light that either they emit or that they reflect. And any light that's emitted by material inside here shoots up and gets pulled by gravity right back down. And any light from the outside there's nothing at the event horizon itself. It's not a solid thing. It's just the point of no return. And so light will naively cross it and get sucked into the singularity and be gone forever. And so there's no way for light to reflect off the event horizon. There's no way for light to escape from inside the event horizon. So the event horizon itself is a pitch black sphere, ultimately, completely pitch black sphere. So Schwarzschild was like, well, even if they do exist, you're never going to see them. But while we can't see the black hole itself, we can't see the singularity, we can't see anything from inside the event horizon, we can see things that are near the event horizon. Things that are doomed on their way into the black hole. We can imagine what the consequences of that are and then look for those consequences. And so the ability to see a black hole is tricky. By definition, the black hole itself is invisible. It's in the darkness of outer space, and it emits no light itself. But a black hole can betray its presence when it consumes gas. And so the analogy I want you to think about is, and in fact right now there's a horror film in theaters. Don't go to a theater, coronavirus, but once it comes out and is available on Netflix, watch it at home in the safety of your living room. The Invisible Man. Someone's remade the Invisible Man movie. How do you catch an invisible man? He's invisible. Well, you throw paint on him. You look for his footprints in the snow or the dust. You find indirect things that betray his presence. And so this is what astronomers have done. Black holes betray their presence when they're eating, when they're feeding on gas. And so gas, as it's falling in towards the black hole, it gets accelerated to really high speeds. And as it's coming in, as it's falling in, there's the black hole, a blob of gas here. These particles are going to get drawn in that direction. These particles are going to get drawn in that direction. So as the cloud gets accelerated towards the black hole, it gets compacted it gets crushed. It gets squeezed together. And when you compress gas, it gets hot. And so as the gas falls in, it speeds up and it gets hot as it is falling in. And as long as you catch it before it crosses the event horizon, the light that hot gas is emitting is visible to us. That light can escape. And the gas is predicted to get so hot that it's going to emit X-rays and ultraviolet light and visible light just before falling past the event horizon of the black hole. You have to feed a black hole gas, and you got to feed it a lot of gas for it to become visible or inferable. For you to see the footprints of the invisible man, the snow has to be deep enough. And so here's how we do it. We get a normal star, and we get a black hole. Black holes result from the death of a massive star. When a massive star runs out of fuel, its center can collapse into a black hole. So if I started out with a binary system of two massive stars, and the first star lived out its entire life, collapsed and died and turned into a black hole, it can still be orbiting its original companion. And then when its massive companion starts to die, when stars start to die, when they're reaching the end of their lives, they start to swell up. And so as this star swells up, it eventually reaches a point where the pull of gravity towards its center is weaker than the pull of gravity towards its black hole companion, and material from the surface of the star starts to flow up and off the surface of the star and towards the black hole. And because of the spiraling motion of the two things in orbit, the gas can't just fall straight in, it has to take a spiraling path in, so it forms this structure that we call an accretion disk. The gas orbits the black hole before it spirals its way in. And that's a good thing for us because this hot gas gets even hotter when it's trapped in that whirlpool as it's getting closer and closer and closer to the black hole. And so this is an artist's impression. This is not a direct photograph. It's an artist's impression of what we think it looks like. Here's a normal star. Here's the black hole. The gas being stolen off the surface of the normal star falls into the black hole's gravity and spirals around, spirals around, spirals around, creates a structure that we call an accretion disk. And that accretion disk gets so hot that it produces X-rays. The gas in the accretion disk is so hot that it produces X-rays. And so this is what we look for. We look for X-ray systems, objects in the sky that are emitting X-rays. We localize, we figure out where exactly on the sky the X-rays are coming from, and then we look there in visible light, and if we see a normal star that appears to be orbiting something that we can't see, and if we use our knowledge of stars, how big, how bright, what color is this star, that tells me the mass of this star, it's orbiting something that's 3 times more massive than it is. If this star is 10 solar masses, then this invisible thing must be 30 solar masses, and yet I don't see it in visible light. I see it in flickering X-rays, but I don't see it in visible light. And if the X-rays are extreme enough, bright enough, if the motion of this star in its orbit around the invisible thing is fast enough, we can rule out every other possibility. It has to be a black hole. And similarly, this would be what we call a stellar mass black hole. This thing might have 10 solar masses in it, 10 times the mass of the sun, compacted down to something the size of New York City. But in the centers of galaxies are things that are hundreds of thousands or millions of solar masses. We don't know how they formed, but they're there, and they're sucking up gas, and we can see them. And there's just no other thing that they could be but a black hole. All right, so Newton derives his law of gravity. He combines it with his laws of motion. He develops his equation for circular velocity. He develops his equation for escape velocity. And so he then turns his attention to Kepler's laws. Can I explain Kepler's laws with my law of gravity? And it was his success at doing it that convinced everyone that the law of gravity was correct. So Kepler had said, when a planet orbits the sun, its orbit is an ellipse with the sun at one focus. That's his first law. Newton generalized it to say when two masses are orbiting each other due to gravity, like the moon and the earth, each orbiting their center of mass, the earth orbiting the sun, the two of those bodies orbiting their center of mass, which is really close to the sun. When two masses orbit via gravity, they both move. The sun is not motionless in the center of the solar system. They both move in similarly shaped paths, not necessarily ellipses, not exclusively ellipses. So they move in similarly shaped paths, And those paths have a shared focus point at their center of mass. The shapes of the orbits, the two orbits, the bigger body, the smaller body, or body number one, body number two, they have identically shaped orbits. Those shapes can be circles, those shapes can be ellipses, those shapes could be straight lines towards each other where they would collide. But there are also other shapes that can be included, and Newton realized that all of these shapes can be grouped into one family called the conic sections, slices through a cone. And what shape you have is set by the speed when the two objects are furthest apart from each other, when they're at their ap point, their aphelion point, their apogee point. The general term is apoapse point. And so, both masses are orbiting their mutual center of mass. That's at one focus of each of the orbits. It's just Kepler didn't notice this because he was looking at the sun being orbited by a planet, and the planet's mass is so much smaller than the sun's mass. The sun's mass is so much greater than the planet's mass that it didn't appear like the sun was moving. The center of mass of every planet's orbit is really, really close to the sun, such that you need super high resolution telescopes to make the measurements to detect the sun's motion. And the same is true for Jupiter's moons orbiting Jupiter or Earth's moon orbiting Earth. The planet is so much more massive than the moon that the center of mass is either inside the planet or really close to the planet, so it's not obvious. And for all the planets and moons that Kepler knew about, the center of mass is inside the planet itself. So we can't fault Kepler for not discovering this stuff. He restricted himself just to the scenario of a really supermassive object like the sun with a much smaller mass object like the planet orbiting around it. So he didn't see these other patterns that Newton was able to show theoretically had to be there. Even though we didn't have a scenario with two equal massed things orbiting each other, this is how it would have to be. So one discovery that Newton made was that not all orbits have to be repetitive closed paths. A plunging orbit ends, it doesn't repeat itself. But a sufficiently elliptical orbit such that the two objects miss each other when they're closest together just repeats itself over and over and over. Ellipse repeats itself over and over and over. A circular orbit repeats itself over and over and over and over. But not all orbits have to do that. So the orbits that repeat themselves, Newton coined the term closed. Those are closed orbits. The orbit starts at one point, loops around, and closes itself off, repeats itself. But open orbits are also possible, too. And so line segments, ellipses, and circles, all three of these are ellipses: an ellipse of eccentricity 1, an ellipse of eccentricity 0, an ellipse of eccentricity somewhere less than 1 but more than 0. Those are all ellipses. Closed orbits are elliptical. Open orbits have two possible shapes: a parabola or a hyperbola. And those two shapes, added together with the three ellipse shapes, are all shapes that you get when you slice through a round cone. And Newton was very familiar with his laws of geometry and mathematics, and so he already knew this family existed. But it was interesting to him that all the orbits could be related to a family of geometric shapes that were simply produced by one imaginary action. Take a round cone, cut through it at a certain angle, I'll produce one of these 5 shapes. And so here I have a round cone. So the light blue thing is a cone, a round cone. All cones start at one point. Their outer edges open at a certain angle, the opening angle. And anytime I slice through a round cone, perfectly perpendicular, to its central axis of symmetry, I'm going to get a circle. So I've got this blue cone. Imagine I've got a giant sushi knife, and I slice through it really quickly. If I hold my knife perpendicular to the central axis of symmetry, parallel to the base of the cone, I'm going to get a circle. If I slice it here, I'll get a big circle, a medium-sized circle, a small circle, a really tiny circle. If I slice it there, I'm going to get a point. And so a conic section is any planar slice through a circular cone. If I take my knife and just touch the edge of the cone, if I lay the blade of the knife on the cone, if I bring the knife blade to it sideways, it's only going to touch the cone in a straight line. So that's one way to slice a cone, is just barely touch it. Just skim my blade along one edge, and I'll produce a straight line. So there's the red orbit, which is a straight line. The closed shapes are the bound orbits, things that stay trapped in the object's gravity. So if these are orbits of things orbiting the sun, then the round orbits are major planets. The elliptical orbits might be asteroids or comets. And anything that has an elliptical or round orbit stays trapped in the sun's gravity. It comes back to its closest point to the sun. It returns to its furthest point from the sun. It just does them over and over and over again. So they're bound by the sun's gravity. They can't escape the sun's gravity. At every point here in this ellipse, if the sun is at this focus, at the focus at this end of the ellipse, my orbiting body is going to be moving fastest when it's here. It's going to be moving slowest when it's here. Even when it's here, moving at its fastest point, it's moving slower than the escape velocity from the sun at that point. And that's its fastest point in its orbit. So every point in its orbit is slower than the escape velocity. So it's never going to escape. Same is true for the circular orbit, for this elliptical orbit. In the straight line orbit, the things just are drawn together and collide. So it's a bound orbit as well, but it isn't a closed shape necessarily. It doesn't repeat. If I cut my cone parallel to the base, like the brown orbit, I get a circle. If I cut at a slight tilt to the base, I get an ellipse. And I can tilt upwards and get an ellipse that way, or I can tilt downwards and get an ellipse that way. So if I'm always cutting from the left-hand side, if I start my knife blade at the left-hand side of the cone, if I cut upwards, I get an ellipse. If I cut horizontally, I get a circle. If I cut downwards, diagonally, I can get an ellipse. As long as this angle here, my downward angle here, is less steep than the far side, then I'm going to come across to the far side. My blade will cut all the way through to the far side, in which case I'll get a distorted circle, an ellipse, for my orbit. But I could cut more steeply than parallel to the far side. I can cut perfectly parallel to the far side. So I touch my knife to the cone on this side, and I hold my knife blade parallel to the opposite side. And that way, when I slice through, this slice is parallel to the opposite side. So as I keep going deeper and deeper into the cone, it's neither getting closer nor further away than the opposite side. So it's never going to touch the opposite side. I'm just going to keep slicing my cone, which means I'm never going to close off. In order to close off, I have to start at one side, and my knife blade has to reach the other side. If I cut the cone too steeply, I won't do that. I have an open-ended horseshoe-shaped orbit where if the sun is here, this is the point when I'm closest to the sun, but if I go backwards in time or forwards in time, I'm just going to go off into infinite outer space. An object on this orbit would fall in, loop around the sun once, and then leave again and never come back. And if I'm slicing perfectly parallel to the opposite side, the geometric shape that I get is a parabola. A parabola is one end of a very, very, very stretched out elongated ellipse. If I grab this point, as you can see, as I slice more and more steeply, more and more steeply, more and more steeply, this point and this point just keep getting further and further apart until eventually, when I'm slicing parallel to the opposite side, this point has dragged out to an infinite distance away. And so a parabola is just the skinny end of an incredibly cigar-shaped, infinitely long ellipse. And so open-ended cuts, very steep cuts through my cone, give me my unbound orbits, my open orbits. And if I cut parallel to the opposite side, I get a parabola. If I cut more vertically than the opposite side, if I cut perpendicular to the base or in between, any slice in between, then I'm going to get a hyperbola, which is like an open-ended ellipse, like an open-ended parabola, only, I'll show you the next slide, the two edges keep spreading out further and further and further apart. So if I look at each one of these orbits from above, look at the shapes from above, then color-coded, they look like this. My red straight line plunging orbit is there. I could imagine shifting all of these so that the point where my knife first touched is the same in every point. So I bring this down to the circle, I bring that point down to the circle, I bring this point up to the circle, I bring this point up to the circle, I bring that point up to the circle. So they're all sharing this one point. That point is there. My straight line plunging orbit is just, my sun is here, and I start with 0 velocity, and I just fall straight into the sun. So this orbit is my straight line plunging orbit. The green ellipse is this elliptical orbit here. I have an ellipse, and where I'm starting is where I'm furthest from the sun, the aphelion point. Then I have the circular velocity, and so I just maintain the same distance from the sun. The sun is at the center of my orbit. I have a constant speed in my orbit. Then the next is the gray ellipse. That corresponds to this ellipse here. I'm starting at the same point, but I have more speed than my circular velocity, so I loop out further away than the circular velocity does and then get pulled back. And so I have an ellipse, but now I'm starting at my perihelion point rather than the green ellipse. I started at my aphelion point. The gray ellipse, I'm starting at my perihelion point. And then the brown orbit corresponds to the parabola, and the blue-gray orbit corresponds to the hyperbola. And each one of these is just determined by, I'm starting at this point, what speed, what horizontal speed, what speed perpendicular to the radial distance do I have? If my speed is 0, I'm just going to fall straight down. So I'm a certain distance away from the center of the Earth. I'm going to let the ball go without any horizontal speed. It just orbits straight down to the center of the Earth and collides with the Earth. So that's a bound orbit, but not one that repeats. If I throw my ball sideways with less than the circular velocity, it follows, here on the surface of the Earth, it follows a parabolic orbit, but that parabola is just a short segment of a really big cigar-shaped ellipse. And so if the release velocity, the velocity at that special point, is less than the circular velocity, I'm going to have an ellipse, and that special point is going to be my greatest distance away from the sun. Similarly, if I just let myself go with 0 velocity, clearly my starting point is my aphelion point, my point furthest from the sun. I'm This is as far as I'm ever going to be from the center of the Earth. If I let it go and let gravity give it an orbit, all it's going to do is get closer to the Earth. So a velocity of 0, you start at your aphelion point, you plunge into the sun. A velocity that's greater than 0 but less than the circular velocity, I'm going to have an elliptical orbit where I'm starting at my aphelion point. If I release myself from that point with exactly equal to the circular velocity of that point, not surprisingly, I have a circular orbit. I just maintain the exact same distance from the sun all the way around, and I just repeat endlessly, 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 endlessly. If I start myself out with more than the circular velocity, but less than the escape velocity, I'm less than the escape velocity. Well, in my circular orbit, this point is neither the aphelion point nor the perihelion point, or perhaps it's both at the same time. The distance from the sun is constant, so it is both simultaneously the most distant point from the sun and the closest point to the sun. It is the fixed constant distance from the sun. And then when I give myself more speed than the circular velocity, but less speed than the escape velocity, I get an elliptical orbit again, only now I'm starting at the perihelion point, the closest point to the sun. I climb far away from the sun, and then I fall back. I have my fastest speed there, my slowest speed out here, my fastest speed here. My fastest speed is slower than the escape speed, so I can't escape the sun's gravity. I get drawn back to where I started. If I give myself exactly the escape speed at that point, then I'm going to fly out into space, but I'm never going to come back. And what you can see about the two arms, so the parabola, the parabolic orbit, the parabola shape, is horseshoe-shaped, but if I follow these two lines, keep extending them out, they just become parallel lines. So there's a maximum separation from this side of the orbit to that side of the orbit. There's a fixed, they'll never be further apart than a certain maximum distance. Whereas if I start at this point with much faster than the escape speed, or faster than the escape speed, that gives me the hyperbolic orbit. And the property of a hyperbolic orbit is that this curve goes out and it approaches a straight line, but it approaches a straight line that's at a sloping angle that way, and this line goes out and approaches a straight line, but it's a straight line that's sloped in the opposite direction. So however far I started away from there, I come in, I loop around once. As I keep going further and further out, I keep getting further and further away from my earlier starting point. Hyperbolas are horseshoes that have been bent outwards, giving them more of a gap. And it just keeps it, the greater and greater I make this velocity, the more wide open these two, those two trajectories become. The inbound trajectory and the outbound trajectory just keep getting spread further and further and further apart, such that if I draw a hyperbola, so there's the sun, there's my best attempt at a parabolic orbit, a parabola. This line and this line are just becoming more and more parallel as we keep going further and further out to the right here. But a faster orbit than that would be a hyperbola like this, and an even faster orbit would be a hyperbola like that, and a really, really super fast orbit would be a hyperbola like that. The object is coming in so rapidly that the sun's gravity just doesn't have a lot of time to bend it. It's got so much forward momentum that the sun's acceleration isn't very strong relative to that forward velocity. And so it zips past the sun at a really high speed, and the sun just doesn't have much time, and its gravity isn't strong enough to turn it very much. Whereas something that's moving exactly at the escape speed falls in, accelerates, right at the moment where it's at perihelion, closest to the sun, it's moving at the escape velocity, and then it starts climbing away from the sun, and the sun's gravity is pulling backwards on it, slowing it down, 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 but it has just exactly enough speed at this point such that the sun will never be able to get it to stop. It will always continue to keep going outwards at just a little bit slower than it was yesterday, but still not zero. A little slower tomorrow, still not zero. Slower yet tomorrow, still not zero. It'll never slow down to zero in a parabolic orbit, but it'll get arbitrarily close to zero as I give it more time. These orbits, the hyperbolic orbits, they just get closer and closer to some fixed exit velocity that isn't zero. And the less bent the hyperbola is, the faster that far, far out destination velocity is. All right, the other part of Newton's version of Kepler's first law is that both objects are orbiting each other, and they orbit a shared focus at their center of mass. So what does that mean? The center of mass between two objects, you can think of it as the imaginary balance point. I've got one object here, I've got another object here. I want to put them on a teeter-totter so that they balance. Where does the fulcrum point, the pivot point of the teeter-totter need to be? If my two objects are exactly equal in mass, well, then they have the same weight, so the balance point has to be exactly halfway in between them. That makes sense. But what Newton was able to show, other people I think before him had derived this, but the center of mass is determined by the fact that the product of this mass times its distance from the center of mass is equal to the second mass times its distance from the center of mass. So R2 times M2 is equal to R1 times M1. If M1 and M2 are equal, then R1 and R2 have to be equal because their multiplier has to be equal. M1 times R1 has to equal M2 times R2. So if the M2s are equal, I can cancel them. If M1 is the same thing as M2, then I can replace it with M2, and then I have an M2 on both sides, so I can divide it out. And then I see that R1 is just equal to R2. If I take this equation and solve for R1, I just want to divide M2 out of both sides. It cancels on the left. And I see that M2 divided by M1 times R2 is equal to R1. Again, if these are equal, this fraction becomes 1, and R1 equals R2. But if this mass is twice as massive as that one, then if this is 2 times bigger than that, then this must be 2 times smaller than that, so that the 2 times bigger, 2 times smaller cancels out of this side, and I get equal sides. So star 1, if it has twice the mass of star number 2, their center of mass is, I divide the center of mass into 3 pieces. I've got 3 units of mass. I've got two mass units here, 1 mass unit there. So I divide the whole distance between them into 3 portions, and I give 1 portion to this one, and I give 2 portions to that one, such that this mass is 2 times larger, but this distance is 2 times larger. So the equation fits. R1, M2 is 1/2 of M1, so this is 1/2. So R1 is 1/2 of R2 for that scenario. And if I have a star with a planet orbiting around it, where the star has mass m, and the planet has 1/100th the mass of the star, this is like Jupiter orbiting the sun, then I now have 100 mass units in the star and 1 mass unit in my planet. So I've got a total of 101 mass units. So I divide my distance between them into 101 equal pieces, and I give 1 piece to the stars, R1, and I give 100 pieces to the planets R2, and then this is 100 times larger than that, but this is 100 times smaller than that. And so the 100 factors cancel. The two sides are equal. If M1 is 100 times larger than that, then this needs to be 100. This is going to be 1/100th, and this is going to be 1/100th of that. And usually that puts the center of mass either inside your star or very close to your star, so it looks like planets are orbiting their star with the star at one focus of the planet's orbit. But the actual focus of the planet's orbit is the center of mass. And the star itself will have a little tiny orbit surrounding the center of mass as well. I'll show you some animations here in a moment, but here's where my center of masses all work out to be. This is 1/2 of that distance. That distance there is 1/100th of that distance. So, if I look at my object here in this animation, the bigger mass is 10 times larger than the smaller mass. So this is a small planet with a relatively large moon, sort of like Pluto and its largest moon, Charon. And so I see that the objects, as they orbit, they're both orbiting the red cross. That's the center of mass. The center of this white disk is following this dashed lined orbit. And so its orbit is smaller than its own diameter, and the large body is just wobbling in place as it orbits, while the small body is following a true, observed, visible, obvious orbit. So from a great distance, it's just going to look like this thing is orbiting that thing. But Newton showed us that they're actually both orbiting. They're orbiting the center of mass. But if the mass ratio is extreme enough, if one object has almost all the mass, then it's going to be really, really close to the center of mass. You can think of the center of mass as the average position of all the atoms. Well, if the planet here has nearly all the atoms, if it's got 99% of the atoms, then of course the center of mass is going to be inside of it, because that's where the average position of most of those atoms is. And so when you have a small mass orbiting a large mass, the large mass just appears to wobble about the center of mass point, which is only slightly offset from its own center. And so this would be, in the case of the Earth, the center of mass is closer to the surface, further offset from the center of the Earth, but it's kind of similar to the Earth and the Moon. And in the case of Jupiter and Jupiter's moons, Jupiter's orbit is just a teeny, teeny, tiny thing, really, really small. 1/100th of the diameter of Jupiter itself. So it's barely wobbling around as its moons orbit around it. If I have similar masses, then I get orbits like this, where here's the center of mass, the red square is the center of mass. I've got an object that's 1.5 times larger than the second object. So if this has 1 unit of mass, this has 1.5 units of mass. And so the average position of all of the atoms isn't inside that one. It's not inside that one. It's in empty space. There are no atoms near the average position of all the atoms. But because M1 is 1.5 times larger than M2, 1.5 times more mass than M2, its M2's distance from the center of mass is 1.5 times larger than M1's distance from the center of mass. And so the bigger object has the smaller, slower orbit by a factor of 1.5. Pluto and its moon Charon have orbits similar to this. So here is, there we go. Here is a computer animation demonstrating Pluto and its largest moon orbiting each other. Pluto is 8.4 times more massive than Charon, and given their complete orbital separation, that means I need to divide the distance between them into 9.4 pieces and give 8.4 of them to Charon and 1 of them to Pluto. And so the center of mass is not inside Pluto. As Charon orbits, Pluto also orbits. They orbit each other. And just like our moon, Charon always keeps one side facing Pluto, but interestingly, Pluto always keeps one side facing Charon. So if I live on the proper side of Pluto, I see Charon floating motionless in the sky. It's just always, it might always be 50 degrees above the horizon to the east from where I'm standing on Pluto. And as Pluto turns once every 6 days, they orbit each other roughly once every 6 days, I'm going to see the stars and the sun go behind it, but it's just going to hang there motionless. That's if I live on this side of Pluto, the side facing Charon. If I live on the opposite side of Pluto, the side facing away from Charon, I don't even know that Charon exists. It's always below my feet at a fixed position below the horizon, never moving. So I'm unaware that the moon is there. All right, so Kepler looked at Newton's third law, and he revised this one to become one of the most valuable equations in all of astronomy. His law of gravity is one of the most valuable equations in all of astronomy. His changes to Kepler's third law are one of the most valuable equations in all of astronomy. Kepler had said that the square of the sidereal period of 2 orbiting objects is directly proportional to the cube of the semi-major axis. So that's what Kepler said. Newton agrees. That's correct. But it's also inversely proportional to the sum of the 2 masses. So if I call m total m1 plus m2, then p squared is directly proportional to a cubed, but inversely proportional to m total. A proportionality, to turn this into a formal equation, I just need to replace the proportionality constant, the proportionality sign here, with an equal sign and throw in the constant. So this sentence says this, but it also literally means this. P squared is directly proportional to a cubed. P squared is inversely proportional to m total. And there's a constant in here to make the units work out right, because these are length units cubed. These are mass units. These are time units squared. So without that, this equation doesn't make sense. I need this to make the units make sense. And the numerical value depends on which units I choose. If I choose meters for length and kilograms for mass and seconds for my length of time, this is going to be some bizarre number, hard to remember. But if I scale everything to the Earth's orbit, like Copernicus and Kepler had done, if I measure my distances in astronomical units, if I measure my time in years, and I measure this relative to the total mass of the sun plus the Earth, then I'm scaling everything relative to the Earth's orbit. And in that set of systems, A is equal to 1, and 1 is, for the Earth, A is equal to 1, 1 cubed is 1, P is equal to 1, 1 squared is 1, so this side is equal to 1, the top here is equal to 1. If I measure the mass in terms of the mass of the sun plus the mass of the Earth is just essentially the mass of the sun, because the Earth is only 1/300,000th the mass of the sun. And 1 plus 300,000th is pretty much just 1. So if I measure masses relative to the sun, how many solar masses worth of material do I have in that orbit? What's the size of the orbit relative to the size of the Earth's orbit? How long does it take the orbit to complete relative to how long it takes the Earth to complete its orbit? Measure time in years, measure distance in astronomical units, measure masses in solar mass units, c becomes 1, numerically equal to 1. So using the Earth data, P is exactly 1 year, A is exactly 1 AU. This is a universal equation. It has to apply to everything. So it applies to the Earth. So I plug in 1 year for P squared. I plug in 1 AU for A cubed. And the only two things I don't know yet are the C and the M total. But I can scale the M relative to the Earth as well. The total mass is the mass of the Sun plus the Earth orbiting it. So the total mass is the mass of the Sun plus the mass of the Earth. If I use my units scaled to the Sun, a star's mass is roughly 1 solar mass because the Sun is a star. A star that's twice as massive as the Sun would have 2 solar masses. A star that's 1/4 the mass of the Sun would have 0.25 solar masses as its mass measurement. So 1 solar mass plus the Earth is 300,000 times less massive than the Sun. So 1 plus 3 times 10 to the minus 6 is essentially just 1. To 5 significant digits, it's just 1. So this is 1, this is 1, this is 1. The squares and the cubes don't matter because it's 1. If that fraction is 1 and this side is 1, C has to be 1 as well in this set of units. So C has a value of 1 solar mass times years squared divided by AU cubed. And Newton's version of Kepler's third law tells us that the time it takes an orbit to complete is related to the size of the orbit and the total mass of the two bodies attracting each other through gravity. If I've got a small body orbiting a large body, it's just essentially the mass of the large body. Jupiter's moon's orbiting Jupiter, M total is Jupiter's mass. The moon orbiting the Earth to 2%, it's just to 2% accuracy, it's just the mass of the Earth there. And so here's an equation where I can look through my telescope and I see two things orbiting each other. I watch two things orbit around each other in my telescope. By taking a series of pictures, I can take a series of images that allow one object to make a complete orbit around the other object. And so I can make a picture of their mutual orbit. So here's object number 1, it seems bigger. Here's object number 2, it seems smaller. I take a series of photographs that let me trace out object number 2's orbit around object number 1. From my images, I can determine the radius of its orbit. The average radius of its orbit is its semi-major axis. So maybe it's further here, shorter here, but I measure at a whole bunch of different places, average them together. I get the semi-major axis A. And if my first picture was there, and then my second one was there, and my third one was there, fourth one, fifth one, sixth one, seventh one, eighth one, my ninth picture is back at the starting point, then I just know how long it took to make one complete orbit. And that's P. So from images in a telescope, I can measure P easily. I can measure A easily. This is just a constant. And so the only unknown in my equation is the total mass in the system. So using a telescope, using pictures taken with a telescope, I can measure the mass of something out in outer space, as long as it's involved in an orbit with something else. As long as I see two things in orbit, I can get the total mass of both things. If it's clear from the orbit that one of those things is really huge and the other thing is tiny, if I have a planet orbited by a small moon, if I have a star orbited by a small planet, then the total mass is just the mass of the bigger thing to a high degree of accuracy. To some percent error, I know the mass of the bigger thing. And so Newton's revision of Kepler's third law is an astronomer's bathroom scale. It's how we weigh celestial bodies by watching smaller objects orbit around them. And so, again, I take a series of photographs, string them together into a movie like this, and I can simply measure what's the average radius of the orbit, what's the total period of time, the length of time it takes to complete one orbit, and once I know P and once I know A, I can calculate M. I can reorganize Kepler's law to solve for the total mass. Same constant, A cubed divided by P squared gives me the total mass. Remember that this is just a constant. Those are units in there. Solar masses are units. You're not meant to plug a mass number into there. You're trying to use this equation to solve for a mass number. There's a variable. You're going to be given A. You plug in A and you cube it. There's a variable P. You're going to get a value for P. You're given a value for P. You're going to square it. You're going to divide the A cubed by the P squared. And as long as A is in AU units and P is in year units, you don't need to worry about the constant because its numerical value is 1. Anything multiplied by 1 is left unchanged. The constant is there to get rid of the units. I need mass units on this side. The years squareds are going to cancel. The AUs cubed are going to cancel. I'm going to be left with solar mass units, and that's what my answer is going to be in. If I do this for a planet, this is Jupiter and one of Jupiter's moons. I'll measure the size of the orbit in astronomical units. It's going to be a really tiny number. I'm going to cube it. It's going to get really small. It's going to take just a few days. For Jupiter's moons, the longest one, for the big four, the four that Galileo discovered, the longest period is like 16 days to go around Jupiter. Measured in years, that's going to be a tiny fraction. Squared, it's going to be a tiny number. So I'm going to take a really tiny number, divide it by another tiny number. I'm going to get a tiny number out, and that's going to be the mass of Jupiter relative to the sun. It's going to be in units of solar masses. So if it comes out to be 0.08, then that tells me that Jupiter has 8% the mass of the sun in it. And using Newton's law of gravity and the Earth's orbit, I can measure the sun's mass directly. We know that to a good degree of precision. The final thing is, did Newton change Kepler's second law of motion? He was able to derive it, and it turns out that this is true. The way Kepler said it, Newton proved that this was true. If I draw a line between two orbiting bodies, it sweeps out equal areas in equal amounts of time, and that means the same thing as it did before. Each object's current orbital speed is inversely proportional to its current separation from the center of mass, but each object's distance from the center of mass is related to the other object's distance from the center of mass. It's a simple proportion of their masses. So it's true no matter how I measure it. Each object's current orbital speed is inversely proportional to its current separation from the center of mass, or it's inversely proportional to its current separation from its partner. It doesn't matter which separation I measure, the total separation between the two bodies or the separation between the center of mass. Their current orbital speed is inversely proportional to either of those distances. If the distance doubles, the speed will halve. If the distance gets 3 times smaller, the orbital speed will get 3 times larger. And so it's just the same in each case. And this is my final slide. In our solar system, we always have 2 objects of unequal masses orbiting each other. A planet orbiting the star, the planet Saturn orbiting the sun. The sun is thousands of times more massive than Saturn. The sun is hundreds of times more massive than Jupiter. The sun is 300,000 times more massive than the Earth. Or you might have moons orbiting planets, but even there, the dwarf planet Pluto is still almost 9 times more massive than its largest moon. So the mass ratios in our solar system are always lopsided. But when we look out into space, we often see stars orbiting each other in binary star systems. And this is what I'm showing you here. It's a computer animation, but this is a totally plausible. We see thousands and thousands of binary stars that have orbits like this. The two stars are orbiting each other. Their masses are roughly equal. In the case of this animation, they're set to be identical. The two stars are identical. Same brightness, same mass, same colors, same chemical composition. Everything we can measure about the two stars suggests that they're identical twins of each other. And their orbits around each other are not round orbits. Their orbits are highly elliptical orbits. And so they're both orbiting their center of mass. The center of mass is motionless in between them, but they get closer to it and further apart from it. And we can see Kepler's second law in action here. When the two objects are closest together, that's when they're moving fastest. And when they're furthest apart from each other, they are moving slowest in their orbit. So this would be their periaps position, and that's their apoaps position. But they're following Kepler's second law. If this distance here is 1, 2, 3, 3.5 times larger than their maximum separation, their velocity here is going to be 3.5 times faster than their velocities at their furthest separations. So we see binary star systems with equal mass components, and here again we can use Kepler's third law to figure out the masses of these stars. I can measure their orbital period. I just start my timing there, end my timing there, so that's their orbital period, my stopwatch reading for those two events. And then I measure their average distance. This is their smallest separation. That's their largest separation. I measure a bunch of intermediate positions, average them all together. That gives me their average separation. I have their P, I have their A. I plug it into A cubed divided by P squared, and that gives me the total mass. It gives me the total mass, but looking at these stars, as I pointed out, they're equally bright. They're orbiting each other, so they're the same distance away from us. They're equally bright. They have the same colors, so they're the same temperature. We look at their spectrum, and we see that they have the same chemical compositions, same fraction of hydrogen, same fraction of helium, same fraction of carbon, et cetera, et cetera, et cetera. So every measurement we can make of the two individual stars tells us that they're identical twins. So it is a reasonably safe assumption that their masses are equal as well. And so I know the total mass. I know the two stars are identical twins, so I just cut the total mass in half, and that's the mass of a star with that brightness and that color. And so I can do this for hundreds of different pairs of stars, both identical twins and systems where one star is clearly very, very massive. It's moving slowly. The other one is moving rapidly in a big orbit around something that's barely wobbling. Then in that case, I know all of the mass, nearly all the mass, is concentrated in the bigger star, so the total mass is equal to the mass of the bigger star. And so I can then, through that way, through statistics, through sampling of hundreds and hundreds and hundreds of star systems, I can map out how bright a star is and how hot a star is, what color a star is, to how much mass it contains. And slowly fill in and populate all the possible brightnesses and all the possible temperatures of stars and equate them with a fixed mass through Newton's version of Kepler's third law. So it's one of the most powerful tools that we have in astronomy. It lets us weigh something without going there and touching it. As long as it has an orbital companion, we can figure out its mass. We can make a good guess towards its mass. All right, so that is enough for today. Take a break, wake yourself up, and enjoy the rest of your afternoon.